the first talk, presented by Hugh Allen. Then we'll have a short break, refreshments, tea, coffee, biscuits, and then Mark Woodland will continue with the second half of the evening, okay? So, I'll hand you over to Hugh.
You've oversold my skill. I'm a self-taught astrophysicist. In fact, I'm not a physicist, I'm an astrochemist.
Do you want the lights down?
Yeah. So, I'm sure everyone knows about this. The very southerly appearance of the Aurora Borealis on Thursday night. And I thought I'd begin my talk with this photo just to show that stars, particularly our star, has an influence on our lives, just like we're going to hear this evening about the lives of these stars. Absolutely beautiful picture taken from Chippenham by Andy Burns, whom I think, Chris, he used to be the curator of the Herschel Museum in Bath, I think. Anyway, so there it is, beautiful red aurora. Right, so yeah, the title of our talk, myself and Mark, is The Lives of Stars. And I've put a kind of subtitle there, A Story Where Mass Matters. And that's because Mark and I sort of talked about it, and we felt that the thread, the theme of the talk, because there's so much to talk about, really, is mass, and really, what effect does mass, and what influence does mass have on the lives of stars? And I hope, certainly by the end of my talk, and I'm sure by the end of Mark's, you'll be convinced by this. So, now there's me. I think some of you have seen this photo before at the last talk I gave at Stargazing Live, but there I am, bathed in starlight, of course. It's sunlight. I just put this up just to show you, this is my telescope. This is what I've used to take all the uncredited images in this presentation. Where I've used somebody else's image, and people who do these things have to be very careful about this, I've always put a credit. But when you don't see a credit, it's an image taken through this telescope. It's an 8-inch reflector. Obviously, in this case, it's got a filter on the front. Never look at the sun directly through a telescope without a filter, please. So yeah, that's why that image is there. And another introductory comment. I just wanted to make sure that, I'm sure most people know this, but where the sun's energy comes from, where does that starlight come from? You probably know that it's nuclear fusion in the core of the sun that fuses hydrogen into helium. That is the source of the sun's energy. And there is the reaction that happens. 4 hydrogen nuclei, which is essentially a proton, 4 protons, fuse together to form 1 helium nucleus, which is 2 protons and 2 neutrons. And that means that the mass here of a helium nucleus is not quite the same as 4 hydrogen nuclei. It's a little bit less. And that difference in mass is turned into energy. And it comes out in 2 forms. It comes out as neutrinos, which are these very esoteric particles that really have only recently been discovered. They hardly interact with anything. They're very difficult to find. And light. And right in the core is where all this takes place. Only in the core. That middle 25% of the sun. This light is in the form of the most energetic wavelength of light, gamma rays. You certainly would not want to be exposed to gamma rays. It takes light thousands of years to work its way out of the core to the surface of the sun. It sort of random walks its way, banging against atoms as it goes, and a few thousand years later, it reaches the surface of the sun, where it's changed into visible light, as we'll see. And for fusion to take place in the core of the sun, you need a temperature of at least 10 million Kelvin, pretty much the same as 10 million degrees centigrade, and huge pressure. Otherwise, this reaction won't take place. Okay? And that's the sun's energy source. And apologies if you knew all this already. Now, I want to make this point too. We live in a natural laboratory. We haven't worked out yet how to make a star in the lab. Yet, nuclear fusion could arrive one day. But we've got a natural laboratory in the sky. You know, there are 100 billion stars in the Milky Way, roughly. And there are probably 100 billion galaxies in the known universe. So that's quite a few stars to take a look at. So you've got to reckon there's a pretty good chance of seeing any kind of behaviour of stars if you look hard enough. And of course we do. We have this huge array of telescopes on the surface of the Earth and also orbiting telescopes. And we can see these stars at every wavelength of light. From the most energetic, I mentioned that, gamma rays, very, very short wavelengths, through X-rays, ultraviolet, into the visible area, which is just this tiny portion here that we can see with our eyes, then into the infrared, microwaves, radio and long waves. You know, I copied this from Wikipedia and I thought this is beginning to look a bit out of date to me because it kind of puts a lot of emphasis on the radio and TV. I put it here now in microwaves. You know, I have orange in this little bit and I have Vodafone here. Anyway, but there you go, that's the spectrum of light. And if you don't believe me that we are absolutely determined to observe stars and galaxies and all sorts of things at different wavelengths, then look at the future. There's lots of stuff now, but look at the future. This is an orbiting telescope. Actually, this one is already in orbit. This is NASA's New Star telescope. This is designed to look at stars in the X-ray part of the spectrum. This is a 10-metre long scaffolding that allows these X-rays to be focused. This is orbiting the Earth now. The next telescopes I'm going to show you are off in the future. This is the European Extremely Large Telescope. Actually, I think it's a brilliant name. And look, this was taken by a chap, so I pinched with his permission, his photo off Flickr, at an exhibition about the telescope in Vienna a couple of years ago. Look at the scale. This is a scale model of a train. This is how big the telescope will be. It's got a 40-metre mirror. It will have 20 times the resolution of the Hubble Space Telescope. And it's here on Earth. It will be in the desert in Chile. This is designed to observe invisible and near infrared. And you've got the James Webb Telescope. Many of you have probably heard of this one, draining all of NASA's money at the moment. This is going to have a 6.5-metre mirror, which sounds small compared to that 40-metre mirror. But you can get it above the Earth's atmosphere, and it can see huge distances, right almost to the beginning of time. And it's an infrared telescope, because that's really where the light is coming from those huge distances. And then the last one I want to show you is called the Square Kilometre Array. And this is a radio telescope, so it's going to observe in these wavelengths. This is an artist's impression, it hasn't been built yet. Again, another 10 years off. We'll have a square kilometre array of radio telescopes that will like link together to provide previously unknown resolutions in the radio spectrum. And so I think will be located in South Africa, one of them, and another one in Australia. So there you go, we definitely live in a natural laboratory. So, to get on to the topic, the life cycle of, well, when I say the life of stars, really you should talk about the life cycle of stars. And this will help you explain how Mark and I have sort of divided up the talk. Some of you probably know stars start life in cold, dark clouds. No stars, these dark clouds are made of dust and hydrogen gas. Hydrogen, you saw already, is the raw fuel of stars. These clouds eventually collapse, and we'll talk about that. Stars are born and they light up the cloud around them in this kind of beautiful way. And of course, this is the famous Orion Nebula, and you can see these beautiful shadows caused by the dust, and the new stars are here in the core of the cloud. Gradually, as that ages, this cluster of stars in the middle blow away the gas and dust around them. This is a beautiful photo taken by Pete Richardson, and you can see right in the middle there this gap developing as these new stars push away their sort of birthplace. And what you're left with is an open cluster, and there are thousands of these in the Milky Way. So if that isn't some kind of evidence that this really is what happens, I don't know what is. There are thousands of them. This is one example. I think this is about 10,000 light years away. And these open clusters, the stars are maybe a couple of light years apart, and that's close enough for them to hang together for a short while, but eventually they drift apart. The Sun was almost certainly born in one of these clusters. And an interesting thought for me is it means somewhere in our galaxy there are our brothers and sisters. impossible almost to know where they are. Because, as I say, these clusters, they're not very tightly bound by gravity. Eventually, the stars will drift away, and you'll see more about that in a minute. Eventually, though, these stars age and begin to die, and that's when you get these red giants. I'm sure people have heard about that. And now we're beginning to move into what Mark's going to talk about, the death of stars, planetary nebulae, supernovae in faraway galaxies and even our own, and the remnants of supernovae. And this is how we complete the cycle. The dust that's in these cold, dark clouds comes from the death of stars. So it really is the life cycle of stars. But what's the evidence for a life cycle? Well, here's just one really simple bit. This is the chemical composition of the sun. It's actually quite a dirty ball of hydrogen and helium gas, isn't it? It's got some oxygen in it, it's got some carbon, nitrogen, silicon, magnesium. So this is evidence that the sun was born in a mass of hydrogen and dust. It's chemically contaminated. And we know why. Because of spectroscopy. When you take a very close look at the spectrum of the sun, can you see all these dark lines? They are the fingerprints of these chemical elements. When you know how to interpret this kind of spectrum, you know by the fingerprint, by the number and intensity of lines, what chemicals, what atoms are there. So this made me think. I thought, well, I bet this chap, I bet if he was interested in astronomy, he'd be interested in this aspect of astronomy, spectroscopy. And actually, it's an area of astronomy I quite like to get into, actually, spectroscopy. I think it's fascinating. Anyway, back to the topic. That makes you think, well, if stars are contaminated by dust that's already been formed by other stars, surely there must have been stars right at the beginning of the formation of the galaxy that are pure, are clean. We never found them. But this, and this was published in Nature last month, this is the cleanest star that's been observed to date. It's got a lovely name, SMSS, I won't read all that out. That actually just tells you where to find it. And this is an image taken from the Digital Sky Survey, and it's pixelated because it's so faint, so few pixels have been able to pick up that star light. I think it's about 1,000 light years away, this star. And it's got virtually no contamination in it. Virtually. There's still a tiny bit, which means that something's been at least once around this cycle before it was formed. But it's believed only once. Okay? Remember, this is really faint, very old star. We know our galaxy is over 13 billion years old, and we'll hear more about that in a minute. Does the cycle have an end? There's an interesting question. Well, of course it does. If you remember that dark nebula, it needs two things. It needs dust, but it also needs hydrogen. And in a galaxy, the hydrogen isn't limitless. There's only a finite reservoir. When there's plenty of hydrogen, you get this kind of appearance. Blue colours, lots of bright clumps where there's massive star formation going on. Eventually, galaxies die. And this is an example of a dead galaxy. All the stars are dying. All the stars are orange, yellow stars. And there's no structure anymore. There are no clumps of new star formation. So yes, the cycle does end. I'm sad to say. Eventually, the Milky Way will die. Star formation will stop, and all the stars will eventually age and die. Okay, back to the life cycle. Something more jolly. This is what I'm going to be talking about. The birth, which I mentioned, of the adult life of stars. And Mark will be talking about the death and the aftermath of death of stars. And I think that fits really well with your sort of expertise, doesn't it, Mark, in some of this extreme astrophysics. Mark is a genuine astrophysicist, I'm not. I'm self-taught. Okay, so I'm going to be talking about birth and adulthood. Oh, by the way, since we're astronomers, we like to observe, I've just ticked in green here the objects that we can see. I was going to say tonight, but I don't think we're going to get any observing tonight. But this time of year, you can see all the ones with green ticks in the darkness. Obviously that one you have to wait till the day. The red ones, unfortunately, are more summer and autumn objects. Right, so, if you don't mind, I'm going to start at the second half of my talk, which is stars when they're grown up. And I want you to meet the grown-ups. Now, there are 7 of them, and I don't know if which one you think is going to win the Oscar, like it's happening tomorrow night, but you can decide that at the end of the talk. But I'll introduce you to them. Here they all are. We've got 7 grown-up stars. 7 stars in adulthood. And I'm going to introduce you to each one. And for me, this introduction is important because it shows that the life of stars isn't just about astrophysics or chemistry. It's about the human aspect of the science of astronomy. And this really is what I want to emphasise in this introduction. Oh, sorry, yeah, those are the ones you can observe and those are the ones you can't tonight. I'm afraid Barnard's star and 61 Cygni are both summer and autumn objects. Right, so let's start with Barnard's star. It's called Barnard's star because it's named after Edward Emerson Barnard. I put his dates there so you can just kind of position him in history. This chap, Brian Ventrudo, I would definitely recommend if you want a fascinating blog, and I think he does his blogs every 2 or 3 weeks, one appears in my inbox. And he beautifully weaves stories about current topics in astronomy. And recently he did one about Edward Barnard. And he described him as the world's greatest self-taught astronomer. I have no idea if that's true, that's just his opinion. But I recommend go on his website, register, and get emails sent to you of his blog. They are fantastic. And Barnard was a self-taught astronomer because he grew up in poverty during the American Civil War. And he actually bought his first telescope from savings of working in a photographic shop, I think. And he won a competition to discover comets. And he discovered 8 comets with this small telescope. And as a result, he made his fortune, got himself an education, and became an expert observer based at the Lick Observatory, which is in California in the US. And he was the first to measure the proper motion of Barnard's star. Now, I don't know how many of you know what is meant by proper motion, but you know, I told you that in an open cluster, stars drift apart once they're formed. Well, it's this drifting motion. Every star in our galaxy is whizzing around the centre of the galaxy at about 200 kilometres a second. But they're not all whizzing in quite the same direction at quite the same speed. So they tend to drift past each other, drift below each other. And you can see this if the star is near enough. And he measured the proper motion of Barnard's star, and it's the star with the largest proper motion that we can see from our latitude. 10.3 arc seconds per year. Now, that doesn't sound very much, and it isn't. An arc second is a 60th of the 60th of a degree, 3,600ths of a degree. But you can measure it, and he did. And this is because the star is only 5.9 light years away from us. Now, you don't need, by the way, the telescope we used was a 36-inch, 3-foot refractor, so it has a 3-foot wide glass lens in it. You can measure this with an 8-inch reflector. And I'll show you, this is my measurement. I have to escape at this point. What you're about to see is the proper motion of Barnard's star. Taken from my front garden. Try again. There you go. Now the exposures are slightly different, but this one was taken in July 2012, and the second one, and it's just flipping backwards and forwards between the two, was taken in July last year. So there's a 1-year gap with the Earth in exactly the same position. So this is nothing to do with just looking at the star in a different perspective. This is true proper motion, 10.3 arc seconds, and you can see it. So it's absolutely true. Stars are moving through the galaxy, and this is a beautiful demonstration of it, I think. Shut it. You know how long I rehearsed not to do that? And I still did it. in the back. Okay. Second star, 61 Cygni. This is an interesting star. It's also got a very large population, about half the population of our star. But it's a binary star. Can you see it's two stars? Separated by 31.4 arc seconds. So still not very much, but still enough to be seen in my telescope. And it really is a beautiful sight in a telescope, this star. The two stars orbit each other once every 700 years, roughly. And this star's proper motion was measured by this Italian priest called Piazzi. And it's called nicknamed Piazzi's Flying Star. He founded this beautifully named observatory on the island of Sicily, in Italy. The National Observatory of the Kingdom of Two Sicilies. And he made his measurements from there in 1806. He also discovered the asteroid Sirius. So he's got a fascinating story. Our third grown-up is the Sun. Surely you know everything there is to know about the Sun? Well, look how many satellite missions there are out in space looking at the Sun. So I don't think we do. But this is what I want to dwell on here. The Sun's mass, this is going to be absolutely crucial for us to understand. It's almost 2 billion tons. Now, that's meaningless to me. So what astronomers do is they give it a symbol, M, and this little symbol here is a symbol for the sun, a very ancient symbol for the sun. So the mass of the Sun, which is about 2 billion tons, is a kind of reference point given that symbol. And this grown-up is able to do what most of us grown-ups can't, and that's lose weight. The mass of the Sun is actually falling by 200,000 billion tons every year. And that's because of this energy production. It loses mass, produces energy. It also loses particles, the aurora. Procyon, known by its Bayer designation Alpha Canis Minoris, which means it's in the Canis Minor constellation. And this kind of designation was invented by a chap, Johann Bayer, at the beginning of the 17th century. And if you know your Greek alphabet, the brightest is Alpha, Beta, Gamma, and so on. Its traditional name, Procyon, comes from the Greek before the dog, because it rises just before Sirius in the sky. And that's a nice link to my next star, which is Sirius, nicknamed the dog star, so just before the dog. It's the brightest star visible from anywhere on Earth. It's the brightest star in the sky. And you can see it from anywhere on Earth, apparently, because it's just overhead, just south of the equator. So unless you're actually in the high Arctic, you can see this star. It's another binary star. You see this tiny, very faint companion? The white dwarf, which, again, Mark might have something to say about. It's incredibly difficult to observe or photograph that. I was really lucky, I don't know how I managed it, but just some camera setting and there it is. The white dwarf companion of Sirius. And here is its orbit, there's the bright star, and the white dwarf goes round every 50 years like this, and we're here, 2014, and the gap is actually getting bigger, so it's getting easier to see this star. Alkaid. It's the furthest star in the handle of the plough. This references our debt to Arab astronomy, because Alkaid means, in Arabic, the leader of the daughters of the buyer. And the buyer was the Arab's way of seeing the pan, the pan of the plough. And the three daughters, and this is the outermost daughter, are the three handles of the plough, the three stars that form the handle. Sigma Orionis is the last star I'm going to introduce you to, just below Alnitak, which is the left-hand star in Orion's belt. And it's actually a 5-star system. A and B are two bright stars, too close to C to separate, but they make up that one bright star. C is this very faint one. D and E make up the other two. And this is becoming a theme here, isn't it? Multiple stars. Did you know that 50% roughly of all stars are at least binary, if not multiple stars? We're quite lucky the Sun is just on its own. Or it might give us some nice sunsets if we had a nearby second sun. So, there we go, we've met the grown-ups. We're going to ask a rude question now, which you shouldn't ask grown-ups. How heavy are you? How much do you weigh? And our unit of measurement isn't going to be, I don't know if that looks like kilos there, I'm not sure, or is that pounds? Our unit of measurement is going to be m naught, it's going to be the weight of the Sun, the mass of the Sun. And there's the answer. You can see I've carefully chosen my grown-ups. they represent a nice sequence of masses of stars. From Barnard's star, which is the lightest star, right the way up to Sigma Orionis, which is 18 times the mass of the Sun. So if you think of the properties of stars, what's the most significant one? Well, it's the brightness, surely. That's the first thing you think of with a star. And I'm telling you that the mass of a star really decides everything about that star's state, its future. Well, you're telling me I'm joking, surely. These blue bars represent the apparent magnitude, in other words, the apparent brightness as we see it with our eyes of all these stars. And where's the relationship between the mass and this higgledy-piggledy change in brightness? But there's a missing variable here. Of course we know what it is. It's distance. These stars are at different distances. And once we take that into account, we have to measure it first. We measure the distance to stars using parallax. And I've talked about this in previous talks. And the first person to do that was a German in 1838. And he used the fact that the Earth goes around the Sun. If you measure a star when you're here, compared to here, you've got a huge distance. About 180 million miles between those 2 points. And you can see parallax. If you stick your finger in front of your eye and close one eye and then the other, you see the background against your finger moving, and that's what we're measuring here. But the distances are enough for you to see stars moving against a distant background of stars. And he measured this for our 61 Cygni star, and he got a distance of 10.5 light years, which is pretty close to the actual value. And just to emphasise how important this is, back in the late 80s, early 90s, the European Space Agency sent up a mission specifically to measure the parallax of stars. There's a new mission called Gaia, which has just gone into orbit. This was its launch in December. This was its first light image of a distant cluster of stars in a nearby galaxy, the Large Magellanic Cloud. This is an artist's impression of it. It will measure the parallax angle of stars to a distance of 3 million light years, which is enough to get to the nearest galaxy, the Large Magellanic Cloud. So, go back to our mass versus apparent magnitude. We now, knowing the distance of these stars, change to absolute magnitude, which is how bright would that star be if it was about 32 light years away. So we'll put all these stars 32 light years away, and we see that. So the mass goes up, and the brightness goes up. Remember, magnitude, those who don't realise it, magnitude goes negative as you get brighter. Don't ask why, it's a long story, an ancient story actually. So, brighter, heavier, narrow distances. Okay? So mass absolutely determines the brightness. Now there are equations, I didn't warn you about this, did I? There are equations in this presentation, but honestly, don't get worried about equations. You should cuddle up to them. Look at them, let them tell you the message they're trying to give you. There it is. What this says is that the brightness of our unknown star, which is L, divided by the brightness of the Sun, which is L0, is approximately the mass of the star divided by the mass of the Sun to the power 3.5. So if you work all that out, a star with twice the mass of the Sun will have about 11 times the brightness of luminosity. So that's serious. But a star with 18 times the mass of the Sun will have 25,000 times the brightness of our Sun. That's Sigma Orionis. And what that means is that most of the light in a galaxy, or in any view of the sky, comes from massive stars. So when you go outside at night and you see all these bright stars, most of them are big stars. You don't see these really faint Barnard stars. You can't see anything with a telescope. Then if you think of the next characteristic of stars, people probably think of temperature and colour. Well, certainly colour. And I was going to go on the internet here, but it doesn't really matter. But the colour of a star is determined by its surface temperature. As a star's surface gets warmer, the peak of its emission wavelength moves to the blue. So hotter stars become bluer. Alright? Hotter stars become bluer. If you want any proof of that, you've just got to look at binary stars. We've got two stars that are at the same distance because they're going around each other. So you don't have to worry about distance. And if they're different colours, because they're so close, you see that difference. It's a very subtle difference, isn't it, the tint of a star. But when you see them close to each other like this, and this is a little project I've been doing recently to look at interesting objects in my zodiac sign, which is Aries. So these are binary stars in the constellation Aries. But I think you can see some lovely colour contrasts. So, mass and temperature. Look, here's mass again. These mass are red bars, and here's temperature, the surface temperature. Absolutely, the mass determines the surface temperature of the star. So tiny stars are very cool.